Hello, in this video I will be looking at trying to do some review on trigonometric integrals. So I'll be looking at two types of integrals. That's the sine to the power of nx times cosine to the power of mx dx, and secant to the power of nx times tangent to the power of mx dx. I should say that if we run into cosecant to the power of nx times cotangent to the power of mx, that's cosec cotangent mix, the technique we use in here can be modified, very slightly modified, and can be applied to that mix. So we didn't look at that one, and we're not going to look at it today also. So back to this sine to the power of nx times cosine to the power of mx dx. The first case we looked at were when n is odd or m is odd. That means that n can be odd and n can be odd, m can be odd, or n can be odd and m can be even, or n can be even and n can be odd. So if one of them is odd, is perfectly sufficient, we can apply the technique that I'll look at with the help of an example in this case. So let's just take an example. I have sine to the power of 3x, cosine to the power of, let's say, 4x dx. So we notice that this is odd. So what I will do is I will split one of them and make a sine x dx, which we'll be using it as our u substitution. So here this will be sine squared x. So if you split one, I had 3 copies of the sine, so I have only one left. Cosine to the power of 4x sine x dx. So that I will say for du. And that means that u will be cosine x. That means that I need to replace this by what it is in terms of a cosine expression. And in this case, it's 1 minus cosine squared x. So this expression, the whole integral, becomes 1 minus cosine squared x times cosine to the 4th x times sine x dx. So now if I let u be cosine x, then this becomes almost du. Of course, it's negative du. So let u be cosine x, then du becomes minus sine x dx. So this is minus du. So this expression becomes the integral of 1 minus u squared times u to the power of 4 times minus du, or minus of 1 minus u squared times u to the power of 4 du. Now this is a polynomial in u, and I can integrate this very easily. Once I integrate this, then I will put cosine x for u. Okay, so this is actually u squared minus 1 times u to the power of 4. That's just simple algebra, which is u to the power of 6 minus u to the power of 4 du. And this is u to the power of 7 over 7, u to the power of 5 over 5, plus c, or knowing that u is cos x, will give us cos to the power of 7x over 7 minus cos to the power of 5x minus 5 over 5 plus c. So that would be the integral of sine to the power of 3x cos to the power of 4x dx. And we took advantage of the fact that the power of the sine is odd. And if the power of the cosine is odd, what we will be splitting off is a cosine function. Now let's look at the case when we have n even. Okay, so that's sine to the power of nx cosine to the power of mx dx. If we run into the case when n is even and m is also even, such as sine squared x dx, so n is even, m is 0, that's even also, or cosine squared x to the fourth x dx, that's even also, and n is even. So we use the half angle formula. So that will be sine squared x is 1 minus cos 2x over 2, or cosine squared x is 1 plus cosine of 2x over 2. So that way the power reduces to a power of 1 in cosine in this case. Okay, so for this, using this one, we reduce the power into a power of less power 1. And this one, if we use this, then it reduces the power from power of 4 to a power of 2. So I'll just look at that one. Okay, cosine to the 4x dx is 1 plus cosine 2x over 2 dx to the power of 2, because this is cos to the fourth x means cos squared x. So the cos squared x is what's inside the parenthesis to the power of 2. So if you FOIL it, what you're going to get is 1 plus 2 cosine of 2x plus cosine squared of 2x dx. If you FOIL it, you're going to get this. And now the next step is to reduce that power. Again, we're going to be using the same half angle formula, this half angle formula. But at this time I have 2x here, so that will give me a 4x, because I have a 2x in here. So that becomes 1/4 the integral of 1 plus 2 cosine of 2x plus this is now 1 plus cosine of 4x over 2 dx. Okay, and this is something that we can integrate. I'll just leave it out. I'll leave it for you to do it, or maybe I'll just quickly show you what this looks like. 2 plus 4 cosine of 2x plus 1, so let me make that 3, plus cosine of 4x dx, and this is 1/8 of 3x plus the integral of cosine of 2x is sine 2x over 2, so that will give me 2 sine of 2x. This one gives me sine of 4x over 4 plus c. So we can simplify this, but that's the integral of cosine to the power of 4x. So when we have even exponents, we use the half angle formulas. There are reduction formulas that we looked at in class. The reduction formula is also very useful, but this seems to be equally useful also. I mean, I can't say one is easier than the other. And now let me look at the case when secant to the power of nx tangent to the power of mx dx is given. In this case, what we would want is what we wish to have to see, which is an easier case, is when n is even or m is odd. So if n is even and m is odd, that's good. If n is even and m is even, that's also fine. n odd and m even is fine. So let me see. I have secant to the power of 4x, tangent to the power of, I don't know, 5x dx. This falls into this category. In both cases, I have n is even and m is odd. So using n is even, and forget that m is odd, it's not relevant if you use that n is even, then what you want to do is you split 2 secants off. Okay, so n is even. N is even. So I'll be using that power of secant is even. So in that case, I will write it as secant squared x times tangent to the power of 5x sec squared x dx. In this case, this is my du. So what that means is my u should be tangent of x, because the derivative of tangent is secant squared. So I have to replace this by whatever the tangent expression is. But we also know that sec squared x is 1 plus tangent squared x. Okay? So then this expression becomes 1 plus tangent squared x times, tangent to the power of 5x times secant squared x dx. So if we let u be tangent x, then du becomes sec squared x dx. So this becomes du. Okay? So that's 1 plus u squared times u to the power of 5 du. So this guy becomes 1 plus u squared times u to the power of 5 du. This is a nice polynomial. You can distribute the u to the fifth and then integrate and then replace. A second case, looking at it differently, as in m is odd, okay, we can apply the same problem. In this case, because m is odd, I will look at it as secant to the, so I will split 1 secant and 1 tangent. If the power of the tangent is odd, you can split 1 secant and 1 tangent off. So that gives you secant cubed x tangent to the 4th x sec x tan x dx. So you're preparing this to be your du. So what would be the u whose derivative is sec u tan u? Well, u is secant of x. The nice thing about this is, let me rewrite this a little bit better. Sec to the 4th x, tan to the power of x. So the nice thing about this is I can replace this tan to the power of 4x by sec squared x minus 1, quantity squared, because that's tan squared squared. Tan squared is this to the power of 2. So if I let u be secant of x, I'll have u cubed here, I'll have u squared, the whole thing squared. So that will work. So let u be secant x, then du becomes sec x tan x dx. So that's nice u. So the whole thing becomes u cubed u squared minus 1 squared du. And this is a polynomial. You can FOIL it, integrate, and then replace. Okay? The case when m is odd and n is even, we looked at a few examples. Okay, we looked at integral of secant of x dx, integral of sec cubed x dx. We looked at integral of secant to the, so we use somewhat a reduction formula for this, or not a formula, but we reduced it. This one has its own nice formula we learned. Remember, the secant of x is natural log of sec x plus tan x plus c. So remember, this is just a clean formula. But based off of that, we were able to do integral sec cubed x dx. So I advise you to go back and look at your notes on this. And I hope this helps to revive your memory on the integrals of the trig expressions. There are a lot of examples that are already on YouTube that I posted. You go to my website www.coastal.edu/Manasseh, and you can look at those examples in section 7.2 in the older book, section 2.2 in our Chimera book. All right, take care. Bye-bye.